Welcome to EPG Pathshala program in Linguistics. We are going to discuss a module from the course Introduction to Computational Linguistics and Speech Processing. The course is coordinated by Professor Pramod Pandey, JNU, and Professor Deepti Misra Sarma from IIIT Hyderabad. The module titled is Introduction to Text-to-Speech Synthesis System. The author of this module is Professor Hemant Patil, IIT Gandhinagar. I am Amardeep Kumar Singh, School of Computer and System Sciences, JNU, and I am going to present this module on behalf of Professor Patil. The outline of this module is, first you will learn what is TTS synthesis system, then how it works, the overview, the type of synthesis techniques, and how the method is evaluated for a different synthesis techniques. A text-to-speech synthesis system is a system which is a text is provided and in response to the text, a speech sound is produced by the computer. The TTS synthesis system must be able to read any given text. It must be intelligible and must be natural sounding. A TTS system takes as input a sequence of words and converts them to the speech. The text-to-speech synthesizer is a computer-based system that should be able to read any given text, whether it was directly introduced into the computer or through character recognition system, that is the OCR system. The speech synthesis field has witnessed much advancement in the last few decades. Due to the increasing application of TTS, research activity in this area is also increasing. The TTS system is widely useful for the people with disabilities. TTS system finds its applications in screen readers to be useful for uses of computer system by visually challenged person. Apart from this, recently new and emerging applications of TTS are developing, such as voice cloning, voice reconstruction for people with vocal disability, aid people with speech impairment, personalized speech-to-speech translation, environment adaptive speech synthesis system, intelligent communicative robots, and personal assistant. It is also used for public announcement at railway stations, in retrieving information over telephone services such as banking services, in car navigation, in call center, etc. In very broad classification, this technology can be divided into two broad categories, which are model-based techniques and statistical parametric speech synthesis. While the model-based technique is an old one, which has several phenomena in terms of articulatory or model-based that models the transfer function of vocal tract based on source filter model, Formant Synthesis, and concatenative speech synthesis. The later one, the statistical parametric speech, is a new one and the mostly used phenomena in the recent times. Now we'll move on to overview of the text-to-speech system. I mean how the system works. The goal of TTS is the automatic conversion of written text into corresponding speech. The speech synthesis field has witnessed much advancement in the past few decades. A general TTS synthesizer comprises of text analysis module and digital signal processing module. Well, these two are the main module of this course, where the first one, the text-to-speech synthesizer, works by converting the text analysis module into transcription and the prosodic information. Well, this two information, phonetic transcription and prosodic information, are then utilized by the next module, which is the digital signal processing module. These two modules are used in order to convert the basic text input in order to transport it into a speech. The first one, the text analysis module, has two blocks. The first one is text to phonetics, which is done in a few segments. For example, the first one is text normalization. The second one is the word pronunciation. And then in the second block, text is converted into prosody. This conversion is done by accenting, phrasing, intonation, and duration. These are the 4 points in which text to prosody works. Now I'll explain in brief how each points of text to phonetics and text to prosody works. The first one is text normalization. Well, a text normalization module organizes the input text into manageable list of words. It identifies numbers, abbreviations, acronyms, and idiomatic and expands them into full text. This is commonly done by using regular grammars. The second one is word pronunciation. Once the sequence words has been generated using text normalization module, their pronunciation can be determined. A simple letter to sound rule may be applied where words are pronounced as they are written. However, when this is not the case, another method, which is morpho-syntactic analyzer, that may be used. A morpho-syntactic analyzer tags the speech with various identities such as prefixes, roots, suffixes, organizes the sentences into syntactically related group of words such as noun, verb and adjectives. The pronunciation of these can then be determined using a lexicon. Now we move on to block 2, which is the text to prosody. The term prosody refers to certain properties of a speech signal such as audible changes in the pitch, which is intonation, loudness, tempo, duration, stress and rhythm. The naturalness of the speech can be described mainly in terms of prosody. Prosodic events are also referred to as suprasegmental phenomena, as these events appear to be time-aligned with syllable or group of syllables rather than with segments. The pattern of prosody is used to communicate the meaning of sentences. The text to prosody block produces prosody information using the text and output of the word pronunciation module. This block can be further broken down into smaller processes that determine accenting, phrasing, duration, and intonation for each sentence. Well, we will describe briefly each of the four phases of this block. The first one is accenting. Well, accenting or stress assignment is based on the category of the word. For example, content words tend to be accented and function words are usually not accented. Then the phrasing phase, sentences are broken down into phrasal units and phrase boundaries are assigned to the text. These boundaries indicate pauses and the resetting of intonation contours. Intonation. Intonation clarifies type and meaning of the sentence, neutral, imperative or question. In addition, intonation also conveys information about the speaker characteristics and emotions. The intonation module generates a pitch contour for the sentences. For example, the sentences "open the door" or "open the door" have very different prosody in terms of intonation contour defined as rise and fall of the pitch throughout the utterance. The first sentence is declarative and has a relatively flat pitch contour, whereas the second is questioning and exhibits a rise in pitch at the end of the phrase. The fourth one and the last one is the duration. Segmental duration is an essential aspect of prosody. It affects the overall rhythm of the speech, stress and emphasis, the syntactic structure of the sentence and the speaking rate. There are many factors which contribute to the duration of a speech segment. Some of them are identity of the phone itself, the identity and characteristics of neighboring phones, the accent status of the syllable containing the phone, its phrase position and the speaking rate and dialect of the speaker. Digital Signal Processing Module, which is the second module of this synthesizer system. The DSP system or the DSP module uses the phonetic transcription and prosodic information produced by text analysis module to produce speech. This can be done in two ways, as this can be seen in this diagram. The DSP module first breaks into rule-based synthesis and unit-based concatenative synthesis. The rule-based synthesis are of three types. The first one is articulatory synthesis, Formant synthesis, and statistical parametric synthesis, while the unit-based concatenative synthesis has unit selection-based speech synthesis. Now, there are different synthesis techniques. Here we will be describing 5 synthesis techniques which are commonly used in the present days. The first one is articulatory synthesis. This is regarded as the best but the most difficult synthesis system. The articulatory synthesis attempts to ideally model the complete human vocal organs, that is, the human articulators and vocal folds that produce speech as perfectly as possible. The articulatory control parameters include lip aperture, lip protrusion, tongue lip position, tongue tip height, tongue position, and tongue height. It has the advantage of accurate modeling of transients due to abrupt area changes due to continuous vocal tract movement. The first articulatory model was based on a table of vocal tract area functions from larynx to lips for each phonetic segment. The articulators are usually modeled with a set of area functions between glottis and mouth. For rule-based synthesis, the articulatory control parameters may be, for example, lip aperture, lip protrusion, tongue tip height, tongue tip position, tongue height, tongue position, velic aperture. Phonatory or excitation parameters may be glottal aperture, vocal fold tension, and lung pressure. Now we'll move on to the second kind of synthesis system, which is sine wave synthesis. Sine wave synthesis is a method where the assumption is made that the speech signal can be represented in terms of sine waves having varying frequencies and also varying amplitudes. This method for synthesizing speech is done by replacing the formants, which is the resonances in vocal tract model, with pure tone whistles. So it is considered that a speech signal can be modeled as the sum of n number of sinusoids. You can see the formula for the sinusoids, and which is taken as the sum of the cos function, where ai is the amplitude, omega I is the frequency, and phi I is the phase of each of the sinusoid component. These parameters are estimated from the discrete Fourier transformation of windowed signal frames. The peaks of the spectral magnitude are selected from each frame. The basic module is also known as the Macaulay quarterly sinusoidal model. However, such a model works well with representing periodic signals such as vowels and voiced consonants only, and it will not work with the representation of unvoiced speech. Now we'll move on to third kind of synthesis system, which is Formant Synthesis. Formant Synthesis is based on the source filter model of speech. It is based on the model that the human vocal tract system had several resonances, and these resonances in the system results in various categories of speech sounds. The vocal tract can be assumed to be a cascade of several resonators in case of speech production of various periodic sounds. However, for nasalized sound, the nasal cavity comes into picture, and the tract can be modeled as a parallel resonant structure. Therefore, there are two basic structures in general, parallel and cascade, but for better performance, some kind of combination of these is usually used. Formant synthesis also provides infinite number of sounds, which makes it more flexible than the other. For example, concatenation method. Well, so now we have come to the fourth kind of synthesis system, which is concatenation synthesis. Concatenative speech synthesis is one of the currently used systems. It is based on concatenating pre-recorded speech to produce the desired utterances. In concatenative speech synthesis approach, there is no need to determine speech production rules. Hence, concatenative synthesis is simply better than rule-based synthesis. Concatenative synthesis generates speech by connecting natural pre-recorded speech sound units. These sound units can be words, syllables, half syllables, phonemes, half phone, diphones, or triphones. The joining of natural speech utterances helps to achieve very high natural sounding speech. However, the joints of speech sound units need to be smooth to avoid abrupt changes or glitches in the synthetic speech signal. The main challenges in this approach are the prosodic modification to speech units and resolving discontinuities at unit boundaries or joints. Prosodic modification results in artifacts in speech which in turn make the speech sound unnatural. Unit selection based speech synthesis technique, which is a kind of concatenative synthesis, solves this problem by storing numerous instances of each unit with varying prosodies. The unit that best matches the target prosody is selected and concatenated. Depending on the unit selected, large speech corpus is required to be labeled, which is very tedious and time consuming. These types of TTS systems are more natural sounding. However, the memory requirement of such synthesis technique is very large and hence may find difficulty in being portable to handheld devices. Well, the last one, the synthesis system which we are going to describe, is HMM based speech synthesis system, which is based on the hidden Markov model. So in this case, instead of storing whole speech database in the method, statistically meaningful model parameters are stored and used to synthesize speech waveforms. To build a unique selection system on one speaker, data requires about 8 to 10 hours of speech database. In addition, syllable or phoneme coverage in database is very uneven. Apart from it, in concatenative approach, system will recreate units from what we have recorded. Furthermore, in this approach, we are effectively memorizing the speech data, whereas in a statistical approach, we are attempting to learn general properties of the speech data. This method, this synthesis system, comes under the category of statistical parametric speech synthesis method. The basic idea to generate average of some similar sounding speech segments. Spectrum and excitation parameters are first extracted from speech database. Mel frequency, substral coefficients, and their dynamic features are generally taken as spectrum, and log F0 and its dynamic features are taken as excitation parameters. Then these features are modeled by context-dependent HMMS. Here, spectrum, excitation, and duration are going to be modeled in the unified framework. After the training at the time of synthesis, first given sentence which has to be synthesized, its corresponding utterance is converted to context-dependent phoneme sequence. Now, we will describe how a TTS system, a synthesis system, is evaluated. TTS systems need to be properly evaluated so that the gap of natural speech and synthetic speech can be identified and should be taken care by developing proper methods in each modeling block of TTS systems. TTS systems evaluation includes finding effectiveness of individual building blocks of TTS as well as final outcome of the synthetic speech. Evaluation of TTS blocks includes text normalization, pitch and duration modeling, waveform generation through Vacador, speech parameter generation algorithm, and many other blocks of system. Quality of synthesized speech has been evaluated primarily using subjective listening tests, for example, mean opinion score. Objective tests are also conducted to give other support to subjective tests and may give other attributes of speech quality which may not be captured by human listeners. The detailed descriptions about evaluation of TTS voice quality is given in lecture module, evaluation of TTS voice, which we will be describing at the end of this module presentation. In this module, a general overview of the TTS synthesis system has been presented. While at the beginning of this module, we have learnt about how a TTS synthesis system works by collecting the text collection and then the data labeling, which we have discussed that it is done in several processes. Secondly, there are well used different synthesis methods for the TTS synthesizer system, especially the concatenative system and the statistical parametric system, which we have described already. Now, at the end of designing a synthesis system, the evaluation part is very much important, and the evaluation can be done by using subjective and objective methods. A whole module is dedicated to the evaluation of TTS, which can be done and which we will describe in other module, which is done at the end of this course. Thank you.